Welcome. In this video, we are going to take a look at the concepts of work, kinetic energy, and take a look at the all-important work-energy theorem. And we're going to start in a very familiar place with Newton's second law, net force is equal to ma. And now we're going to replace A with stuff, and that stuff is going to come from the kinematic equation. We have V final squared is equal to V initial squared plus 2 times A times delta x. So moving everything but A over to the other side solves for A, and we end up with the net force is equal to the mass times V final squared minus V initial squared all over the quantity of 2A. And, oops, sorry, not A, how about delta x? Delta x instead, I like that better. Okay, so now we're going to do some slight rearranging. I'm going to multiply both sides by delta x, so we have the net force times delta x is equal to, both of those v squareds are divided by a 2, and they're both multiplied by an m, so 1/2 m times v final squared minus half of m times v initial squared. And here we have it. So Newton defined that left-hand side of the equation, which is force times displacement, as the work. And he defined this part of the equation, 1/2 mv squared, as the kinetic energy. And on the right-hand side, we specifically have the final kinetic energy, because we're looking at v final squared, minus the initial kinetic energy. And we'll get into that. So we're going to take a look at each side of this equal sign a little bit more in depth. So we use the terms work and energy in everyday life all the time, and they have very specific meanings in mechanics. So work is defined in physics as a transfer of energy, either into a system or out of a system. All right, and energy is defined as the capacity to do work. Basically, if a system has energy, it can give that energy to another system. Work then is just a transfer of energy, and energy is the capacity to do work. And if that seems circular, then it totally is. All right. Specifically, kinetic energy is energy of motion. Anything with mass that is moving has kinetic energy. You can see from the equation, since the velocity is squared, we're always going to get a positive answer there. It doesn't matter what direction the object is moving, its kinetic energy will always be the same. If it's moving left, right, up, down, we just do 1/2 mv squared. So kinetic energy is a scalar quantity that can only be positive. Something either has kinetic energy or it does not. All right, let's look at the units on these. We have the units for work, force times displacement. So we're looking at newtons times meters. And on the other side, we have kilograms times velocity squared. So kilograms times meters squared over seconds squared. And it doesn't look like those two are equal to each other until we remember that the newton is a derived unit itself. It's a kilogram times a meter divided by seconds squared. We're multiplying by another meter, so we get kilograms meters squared over seconds squared. So indeed, they are equal to each other. Kilograms meters squared over seconds squared is a mouthful, so we've given it its own name. It's called a joule. And we abbreviate it with the handy-dandy capital J. All right, so that's the unit for work. That's also the unit for kinetic energy, and more generally, any kind of energy. Right now, we're just focusing on energy of motion. So now, because the left side of our equation has the net force times the displacement, then this is a quantity called the net work done on an object. So anytime we're looking at net force times displacement, we get something called the net work. That can be distinguished between the work done by individual forces. So let's take an object in free fall, and it's got mg going down, and then let's say there's a drag force going up that cannot be ignored. So if we're going to talk about the net work, then we would take the net force here, mg minus the drag force, and then multiply that times the displacement of the object to get the net work done. Now we can also talk about the work done by just the gravity force, or we can talk about the work done by just the drag force. And we're going to get into more detail on that later, because it's actually a relatively complex beast, because force is a vector, so is displacement. We've talked about how to add vectors together, but we have not talked about multiplying vectors together. This is a specific kind of vector multiplication called a dot product, but more on that later. Just know that there's a difference between the net work done on an object versus the work done by an individual object. All right, so when we set that net work equal to, let's just write it as work net equal to K final minus K initial, we have the work energy theorem. So specifically we can write it like this: the net work is equal to the change in the kinetic energy of an object. And this is really, really handy when we're asked to calculate what is the total work done on an object. All we have to do is find the change in kinetic energy. All right? And it leads to another little complication, because we said that kinetic energy is always positive. It's a scalar quantity, right? Work is also a scalar quantity. However, because it's equal to the change in kinetic energy, thinking that we can either add kinetic energy to a system, speed it up, or we can take kinetic energy away, we can slow it down, then that means that the net work can either be positive or negative. So what does it mean when the work net is positive or negative? So work net, if it's positive, then we're talking about adding energy to the system, in this case specifically kinetic energy. All right, so we have a positive change in kinetic energy, which is speeding up. So if we do work on a system to speed it up, then we are doing positive work. So car runs out of gas and you and your friends are pushing it to the gas station. You're pushing on it and it's speeding up from rest. So you guys are doing positive work on that car. When it gets to the gas station, you guys stop pushing and friction slows it down. We are taking energy out of that system. All right, so that would be negative work. So if we have negative net work, then we're talking about a negative change in kinetic energy, which is slowing down. Plain and simple. And if you're pushing and pulling on stuff and nothing's speeding up and nothing's slowing down, then there's no net work being done on the system. All right. So Physics 1 students, I want you to kind of put your hands over your ears for a second, because this is just for the Physics C folks. On the left-hand side over here, we have a delta x. This works great if the net force acting on an object is constant, and we want to find the work done. But if the net force is not constant, then that delta x changes to a dx, meaning that we're applying a certain amount of force over an infinitesimally small displacement. And we instead get the work done is the integral of the force with respect to the displacement. All right, so that's a more thorough look at that left side of the equation. And again, we're going to be taking a deep dive into what that means later. So here we have it, the work energy theorem. When we do work on a system, we either add energy to it or we take energy away. Positive work, gain in kinetic energy. Negative work, a reduction in kinetic energy, slowing things down. All right, that's it for now. I'll see you next time.